Now,
Is it the small r represent?
the small r represents the correlation. We're going to figure this out in a second. It's going to mean more to you in a few moments. R represents the correlation coefficient for the sample. Rho represents, the Greek letter rho represents the correlation coefficient for the entire population, for every subway fare and every pizza slice, right? So we're going to take a look at how this is calculated, how this statistic is calculated. Okay, let me let me actually delve into the PowerPoint. Okay, let's see if it opened up. I think I'm going to have to. Here we go. That should work now. Yeah, it was back there. Okay, so find a better picture of this. Guess I'll start with this since I'm gonna run into it anyway. Yeah, don't like that picture. I'm gonna need this. If I were going to compare these two, one of the ways that I would compare this is that I would say, well, within the first year in our study, the cost of a slice of pizza costs so much, and the cost of the subway fare costs so much. I'm going to associate those two. I'm going to call one of them my X and the other one my Y. Now, at this stage, when we're talking about correlation, it doesn't matter which one we call X and which one we call Y. And the reason for that is that when you talk about correlation, it doesn't mean that necessarily that you believe there's causality involved. In other words, we probably, in most cases, would probably say to ourselves, I don't really believe the MTA is conspiring with pizza makers to raise the fare, but prices are going up in general. Maybe there's some reason why transportation costs may have some association with, the cost of doing business in a pizzeria and so on and so forth. There sounds like there's some association, but perhaps one is not causing the other. But now, if I were to take each one of these prices that we were looking at, get that out of the way. I'm going to try and do this so I can see both of them at the same time. There we go. Okay, so I'm going to draw a graph here. Okay, I'm going to call this $2, $1, and 0. And I'm going to call this, on this axis, I'm going to call this the cost of pizza. And on this axis, I'm going to call it the cost of a subway ride. Okay, and I'm going to go, let's see. I'm going to make this a little wide. Okay, I'll make this a little bit more generous. Okay, and I'll say 1, 2, 3, and so on. So if I'm going to look at this first time here, the cost of a slice of pizza is 15 cents. Subway ride is 15 cents. Well, I'm going to turn that into a coordinate on this graph. So I'm going to call the pizza my y-axis, and the subway, I should have done the other way, right? Because usually you see the x-axis listed there. So the pizza is my y-axis, and the subway is my x-axis. So this is 0.15 and 0.15. So on the x-axis, which is subway, I'm going to reverse this just to make it easy for us to interpret. On the x-axis, a 15-cent pizza, when the pizza would cost 15 cents, the subway ride cost 15 cents. So it's 15 cents in the x-axis, 15 cents on the y-axis. 0.15, comma, 0.15. So now I'm going to do it again for the next time I have data for it, 35 cents and 35 cents. Now we're about here. Okay, and then I'm going to do it again for $1 and $1. Okay, then I'm going to do it again. Oh, wait a second, it diverged a little bit here. Pizza costs $1.25, but the subway ride cost $1.35. Went up a little bit faster. Okay, maybe this was here. Okay, and then 175 and 150. This went up to 175, and the subway ride was a bit lower. It was only at 150. Okay, and then finally I have some data at 2 and 2 up here. Now notice this. If I draw a straight line, it appears to me that there's a linear relationship here, because if I join these with a straight line, well, I don't hit every one of these dots, right? You need 2 points to form a straight line minimum. I don't hit every one of these dots, but they seem to come very close to that line, right? So this line, if the way I want to draw that line is I want to draw this line so it's the best representation of the relationship between those two. And again, in statistics, we have a tendency to like avoid negative numbers by doing a lot of different things. And in this case, what we're going to do is that we're going to balance this line. So all of the differences between the value on the x-axis, the pizza, and the value on the y-axis, all of the places where there's an excursion from this line, I'm going to call that little bit of a difference. I'm going to call that my error for the moment. Okay, so this line, this one's here, this one's here. So we have all sorts, we have several different differences, some on this side, some on the other side. But we want that line to be drawn so that the squares of these differences are equal to 0. So we balance the squares of the differences that are below the line with the squares of the differences that are above the line. So we get kind of a middle value for this line. Okay, so in this relationship, there's very close association between what's on the x-axis and what's on the y-axis. Now, if I had reversed these two, the association would have been the same, right? Just would have been, a little bit different in terms of the way it might appear, especially on some others where it wasn't so clear a slope here. So we're going to look at relationships like this. And these relationships are going to take a number of different forms. So, for instance, I might have a situation like this, where I have an x-axis, some value on the x-axis, some value on the y-axis, and I get a result like this. Okay, and just a straight line goes straight across, right? So how does the x value affect the y value? When the x is low, the y is whatever this is, right? Whatever value that is. When the x is large, the x is the same value. So what influence does the x value have on the y value? None, right? There's no association between what the x value is and what the y value is. The x value, no matter what it is, has no effect on the y value. We're going to define that as a correlation coefficient, our R, or rho if you're talking about the population. We're going to define that as rho, R value equals 0. That's no association. Okay, so now I'm going to take another situation here. Okay, how about if it looks something like this, where every one of these dots lies on a straight line? That's a perfect association, right? What can you think of that might have a perfect association? Right? How about BMI and weight? Right? Why would it have a perfect association? Well, because it's a component of it. It's part of the same formula and stuff, right? Or might be something like a scale, pounds to kilograms, right? Just a conversion, right? There's nothing involved there that would introduce any variability here, right? So we would call that a perfect association. So our Pearson's correlation value for that, R is equal to 1. Well, we could have a situation where we're looking at something that might have an inverse relationship. As one goes up, the other one goes down. So that might look something like this. Okay, here's a perfect association here. So what do you think we might give? What do you think the value R might be there? It's -1, right? That's good. The negative is important because that shows that there's a negative association. One goes up, the other goes down, but it's still a perfect association. So now we're left with everything else in between, which is, say, something like this, which is a weak association, something like this, which is a slightly stronger association, still not perfect, right? So all of these other numbers can have values from -1, right, through 0. Let me get this right. -1 through +1. I think I got that right. You're going to have values between -1 and +1. 0 represents no correlation. Anything less than 0 represents a negative correlation. Anything greater than 1 represents a positive correlation. So in this case, which of these do you think might have a correlation coefficient equal to 0.8? Would it be the left one or the right one? I'm going to say one of them is 0.8 and the other one is 0.3. Which do you think? Which one has the 0.8? Is the one on the right or the left?
Right.
On the right, yeah, because that's the stronger correlation. That's the one that's closer to 1. A correlation coefficient of 0.3, right, is a weaker association. CD scattered more. Well, the other place you might see a 0 association is going to be when you have just random values all scattered all over the place. Even though it's not a straight horizontal line, there really is no line that really meets this and creates a usable correlation. So you might see something like this. Okay, so now, how are we going to calculate this? Right? This is going to get a little bit more complicated now. Well, I'm going to show you the way that we do it in SPSS first. Then we're going to come back later and just run through it quickly manually to see how this might work. So I'm going to copy this into SPSS. And you actually, I think I might have put the SPSS file there. I'm not sure. Okay, good. Oh, I didn't want to include that line. Good. Go to my variable view, and I don't remember which one's which. I think pizza's on the left. Pizza and Subway. So maybe it's a good opportunity to talk about how to set up the data fields in here. Notice that it thinks that these values are categorical variables, right? Kind of odd, right? Because they have decimal places and so on and so forth. That's wrong. They're not categorical variables. They're numerical variables. So one of the things I'm going to have to do when I go back into the variable view, is I'm going to have to teach SPS what these values are. So for the first one, I change the default variable to pizza. And for the second one, I'm going to give it the variable name Subway. Okay. Now they're not string variables, they're numerical variables. So I'm going to change that to numerical and numerical. Probably picked up a space when I pasted it in from SPSS. That's probably why I thought it was a string variable. So the width is the number, basically the number of digits that are present. Okay, I'm going to leave it at 6. Decimals was 2 decimal places there. Right. Okay, see what it looks like so far. Okay, that looks good. Okay, but it still thinks it's categorical variables. Okay, so I get up to the label. This gives me an opportunity to tell SPSS to, when I make a table or a graph, to make it a little bit more descriptive. Okay, now you can do this with your data also. Okay, so I'm going to call this cost of a slice of pizza. Right, so it doesn't just put pizza in there with no other explanation. And I'll say cost of Subway fare. Okay, so they're not categorical variables, so I'm not going to put values in here. We only put the values in for their more categorical variables, male and female, so on and so forth. This is actual numbers. So we don't have any missing values. You could just leave it none. SPSS will handle it if it's just blank by itself. Alignment, you can dress this up if you want to, but the important part here is what kind of variable is it. So I'm going to click on here, and we know that this is a scalar or numerical variable. I'm going to click on here and tell it it's a scalar variable. One of the reasons you have to do this is to make sure that SPSS will do the analysis at all. If we try to do a regression and a correlation analysis now before we change that, it might refuse to do it because it might think that they're categorical variables, trying to keep you from making a mistake. Okay, so the first thing I might see, we already kind of plotted this ourselves, but if we were looking at this data for the first time and you wanted to take a guess at whether or not there's a correlation here, an association here, what's the first thing I did when I wanted to see if there was an association? What's the very first thing I did with that data? I plotted it on a graph, right? That graph with those XY coordinates in SPSS is called a scatter plot. So I'm going to go into graphs. I'm going to go into simple version of a legacy dialog, go down to scatter dot, and simple scatter dot. And then I'm going to define it, tell it what variables. So I think I put on the x-axis, I put Subway, and on the y-axis, I put a pizza, cost of a slice of pizza. Now you can go in there, you can tickle it, give it titles, and so on and so forth. But for the moment, I'm just doing this because I want to see if there's an association. So I'll click OK. Let's see what comes up. Okay, here's our graph. Okay, so boy, that looks like a pretty good association. If you want to get a better look at it, as a little cheat, you can double click on this, and it will plot that line for you. If you go in here to where it said add a fit line at total, if you click on that, it will actually add that line. Okay, in fact, it actually does some statistical calculations. Try and ignore those numbers on here because we're going to be getting to them as we work forward. So you can see that this is a pretty good association. So we're encouraged now to take the next step. So what's the next step? Well, the next step is to actually see if there's an association. So our null hypothesis here would be that there is an association, there is no association between the cost of a subway ride and a slice of pizza. Our alternative hypothesis in words is that there is an association between the two of them. And another way to state that would be to say that the correlation coefficient, saying that there's no association, that means that the correlation coefficient must be equal to 0. There's no association means the correlation coefficient is 0, right? Do I use R when I phrase this as a hypothesis? No, I use rho, right? So my null hypothesis is the value rho, which is for the population, same as R, but for the population. Rho is equal to 0 is my null hypothesis. Rho is not equal to 0 is my alternative hypothesis. Could be a negative association, could be a positive association, but it doesn't really matter to us, right? So I'm gonna just so you can see that it's not gonna make much difference. I'm gonna go in here and I'm gonna create another scatter dot, except this time I'm gonna reverse the axes. Is that rho is not equal to 0.
Alternative is not equal?
is not equal. And remember, the null is always equal to, right? Yeah, that it's equal to 0. The null is always that there's no association. And the alternative is that there is an association. And how do you prove an association? You prove that rho, R, is not equal to 0.
That's the big
Yeah.
R, right?
See, and yeah, you can see that it really didn't make that much difference. One of the things you got to be a little bit careful about here is that when you look on this, it looks like a perfect 45-degree angle here, right? It also, you can get fooled a little bit because when you try and observe that relationship, because if the axes were different, it might look like quite different. So for instance, the cost of a slice of pizza were in dollars, but the cost if the cost of Subway were in dollars, but we were putting the cost of the pizza, we were talking about pizza in Italy in 1980 when they were using lira, and it was like 100 lira to a dollar. Well, this would look much different because the axis is different. Because then, like a dollar would be equivalent to 1,000 lira and stuff like that. So the axis would be really weird looking. So it might not. So it might look like this. It might look like this. It might look like that. Depending on the axes are. So you got to kind of ignore that for the moment and just focus on the fact how well do these things fit the line. Because even if you converted this into lira, it would fit the line just as well. But the line might have a different slope. Okay, so try not to pay too much attention to the actual slope that you see there, because we're going to, it will be meaningful to us soon, right? But for right now, just concentrate on how well it fits a straight line. So remember, we're talking about linear relationships here. This is not the only kind of relation that you might run into. You could also run into relationships that might look something like, let's see, where did my notebook page go? It went away. Okay. Why I lose that page more often? Oh, there it is. Okay. Okay. So how about if we have a relationship like this? Okay, and let's see, this is X, this is Y, I won't worry about what they are. Okay, here's a value here, here's a value there, there's a value here. Oh, actually, I don't want to do it that way. I could do it that way. Okay, what's happening here? Okay, here's a set of values, and I'm going to try and fit them as best I can. And it may look something like that. What do you think they call that kind of relationship? There's a correlation there. There's an association between X and Y. They seem very closely associated, but it's not linear. This is called curvilinear, surprisingly enough. It's curvilinear. If it looks like something like this, it's curvilinear also, but it's a special kind. And we see a lot of these kind of relationships. Right? Well, this one is exponential. Right? It's not a straight line. The analysis that we're working with now, today, is all going to be strictly linear relationships. You can sometimes get around that. So a relationship that looks something like this, like the one I just drew, which was exponential, I'm making them not all fall on the line, just to show you that there's always some variability when you work with real data. It's not a perfect association. That is something that we wouldn't be able to work with normally as a linear relationship. But you know something? If we took Y is increasing exponentially. So if we took this and plotted instead of this the log of Y versus X, that might turn it into a straight line. Right? And we could associate this with a linear relationship. So that's a little advanced. We don't have to worry about that. We're only going to apply this to values that right off the bat are going to be going to have a linear relationship. Okay, so let's go back to what we were looking at here. And there we go. Okay, so now we're actually going to calculate the value of the Pearson's correlation coefficient. So how are we going to do that? Now, when we do it mathematically in Excel, you're going to have a better idea of how this is calculated. But for right now, let's just let SPSS do the heavy lifting. Analyze. I'm going to go into correlation. And then I'm going to go into, what do you think? How many variables we have? 2. So what do you think we're going to choose here? Bivariate, right? Okay, so notice that there's only one box on the side there. If I put in one of the variables, it's waiting for me, won't let me say okay, it's waiting for me to put in the variable that I think is associated with it. There's a number of different correlation coefficients. We're going to stick with Pearson's. Okay, I don't think there's any, no, I don't have to worry about that. Okay, so I'm going to say okay and see what we wind up with. Okay, so now the table that we wind up getting, this is really a 2x2 table. You see on the side here, it says cost of a slice of pizza and cost of subway fare, and going down we have cost of a slice of pizza and subway fare. If I go across here from cost of a slice of pizza to cost of a slice of pizza, what's the correlation coefficient for itself? It's 1. Makes sense, right? It's perfect. The cost of a slice of pizza is perfectly correlated with the cost of a slice of pizza. Well, if I compare subway fare to the subway fare, it's 1 also. I just want to point this out because when you see this in Excel, like in the analysis in the post hoc tests, it's constantly doing side by side comparisons for every permutation, even though a lot of them are meaningless. You remember in the ANOVA test, it would look for do an analysis of variance for the same thing, right, in 2 places. Okay, it would just keep repeating it, so it covered every possibility. But what's the real association here? Well, the real association, cost of a slice of pizza to the cost of subway fare, is 0.988. What do we say about the correlation coefficient? First of all, it's a positive number, so that means it's a positive correlation, and it's very close to 1, which means it's a very strong association. But now, we only had a few data points. So even so, it may say that the correlation is very high. Have we really proven with 95% certainty, with less than 5% chance of being wrong, have we really proven that it's not 0, right? Over here, it seems pretty obvious that we've proved it, right? But what if you got a correlation coefficient of 0.3? That tells you, what does that tell you? That tells you there's a positive association, a positive correlation between the 2 variables. However, it's not a very strong one. And since all of this depends on the sample size and how strong the association is and so on and so forth, how can I be sure it's really not 0? Well, we have to do a statistical test. We have to take that R value and the degrees of freedom, our sample size, and we have to calculate how likely it is that we would be wrong if we reject the null hypothesis, R is equal to 0. So in this case, the significance, the p-value, is less than 0.001. So they put 0.000 in here, right? So that's less than 0.05. So we can reject the null hypothesis, both null hypotheses. We can reject the null hypothesis that we state mathematically, rho is equal to 0. We can reject that and say rho is not equal to 0, the alternative. And we can reject it in words. The null hypothesis, there's no association between the cost of pizza and subway ride, and the null hypothesis is that and the alternative hypothesis that there is an association between the cost of pizza and a subway ride. Okay, so we've done our job. We've proved that there is an association here. Is it causal? We don't know, right? We don't know. We might be, might not be. If you look on a lot of published papers, they in fact may even not commit in the paper whether it's causal. They may just report the association unless they're prepared to back it up with some other data or some medical evidence or some reasoning, some scientific reasoning that would suggest that one causes the other. The example of this I like to give in the past was, is there an association between the amount of damage that's done in a fire and the number of firemen that respond to the fire? Is that a yes or no? You think there's an association? The amount of damage in dollars, and the number of firemen that respond to the fire. Well, yeah, a big fire, you get a lot of firemen, right? Is it the firemen causing the damage? Not sometimes. I don't know if you've ever seen them sometimes, but usually it's not the firemen, it's the firemen doing the damage, right? So yeah, there is an association, but it's not causal. It's just coincidental that bigger fire, you get more firemen. Okay, so doesn't have to be causal. So we're going to take a quick break because you got to feed the meter, right? Oh, I'm sorry. I would have stopped a little earlier. See, we didn't miss anything. I didn't see you go. Okay, in that case, I'm going to go a little bit longer, and then we'll take a break. Okay, so now, so I lost my train of thought. Okay, so that's pretty simple for me to do, I guess. Okay, so yeah, I know what I was going to say now. Okay, let me get back to that Blackboard if I can find it. Let's see which one is here. Nope, that's not Blackboard. Here we go. Okay, I put a link here to a fellow that has a website that he looks for spurious correlations. Spurious meaning meaningless correlations, right? Or accidental correlation. I'm going to open up an article on it. It's from the Mirror, the London paper, the Mirror. It's a tabloid. So if something weird comes up, don't blame me for it. They have, I mean, this is the kind of paper they have like reports of alien abductions and stuff like that. So here's an article about this guy's website. Oh God! See, I told you this stuff was going to come up. Secrets from the Sound Suite. Okay, so here. So, more people eat cheese, the more people are killed by their bed sheets. Okay, and wait a second, we're going to get into some others of this that this guy has published. Here, the age of Miss America correlated with the murders by steam, hot vapors, and hot objects. And here he has graphed its data in detail. And what do we see down here? A correlation, right? A very strong positive correlation. See a couple others of these. Per capita consumption of cheese correlated with the number of people who die by becoming tangled in their bed sheets. Now I can imagine Tyler or whatever his name is. I think it's Tyler. I can imagine him, going through, Department of Health morbidity and mortality data and so on and so forth, and just pulling data off of it and randomly running correlations until he could find these kind of, and whatever's from USDA and whatever else and so on and so forth. But some of these are pretty interesting. So what is that? What does this really tell you about this whole thing? It really tells you that a lot of these associations, there's other reason for them to happen other than the particular variables that you're looking. That doesn't mean that there's not an association. It's just not causal with that particular variable. U.S. spending on science, space, technology, and suicide by hanging, strangulation, and suffocation. Look at the size of the correlation there. Right? Look at the. Okay, now notice this is the Mirror. The Mirror did not give us what? They told us the correlation from his side. What did they not tell us? That as statisticians, we should immediately say, well, I can't, this doesn't mean anything without that, right? What's the null hypothesis here? Null hypothesis is that there's no association, right? The alternative hypothesis is that there is. Another way of saying that is rho is equal to 0 or rho is not equal to 0, right? But in order to reject the null hypothesis, rho is equal to 0, what do we have to know about besides that? We have to know the p-value, the probability we'd be wrong. So we could get a very nice correlation of this one over here, for instance, 0.87. But who knows if statistically, mathematically, we can say that is not, there's 95% certainty that it's not 0. So we really can't reject the null hypothesis here unless we see that p-value as well. Okay, and if I go back to SPSS, we're going to, oh, by the way, just so you know, I have on that, I have also there, I should have the link to his actual site. So you can see all the others. I just put that up there because they were, he wrote a book. This is new. I hadn't seen that. So he's published a book, if you want a book on these things, right? So you can see all of these here. And I think, here's his sources, U.S. Department of Agriculture and the CDC. So he has legitimate sources, not like they're not legitimate sources. The divorce rate in Maine and the per capita consumption of margarine. I wouldn't. Yeah, hot vapors and hot objects.
Does that have anything to do with that's age of Miss America? Does that have anything to do with?
Yeah. In other words, in years when Miss America is older, you then have more murders by steam, hot vapors, and hot objects. Yeah, exactly. And I mean, look at these graphs; they're stunning, right? And the correlations. Now, I don't see here, but look at the sources are legitimate. But again, oh, here you go. R equals zero, but R is the correlation. I mean, no, he doesn't give us the unless. No, he doesn't give us the p-values. Right now, could you find out the p-values? He's only got a few data points here. You could actually copy these data points into SPSS, and you could do your own analysis. Right? Maybe one of you might do that and see if he's really accurate. Oh, here you go. I don't know if one person maybe. So at any rate, yeah. But he's doing the same thing we're doing, right? And this is uranium math doctorates awarded in uranium stored in U.S. nuclear plants, and so on. And he's just done. I'm sure he's done millions of these things. And as a matter of fact, there used to be a lot more of them on here. But you know why there's not a lot more of them? Because he wants you to buy the book. I don't know. I haven't read the book. I didn't realize that it was that he had written a book even. Why would somebody give something like this 1 star? Did they take it? Oh, this person took it seriously. Obvious errors are made on 2 separate occasions. I don't know. He cites. I guess this guy went back to check his numbers. Okay, so at any rate. Okay, I don't want to waste too much more time on this. Okay, so at any rate, you see where we're going with this stuff now. Okay.